Good morning, Calculus 2. Can everybody hear me? The audio coming across?
Yeah, that sounds fun.
Thanks. Now, I've gone ahead and posted uh, an announcement about the first test to basically provide more flexibility. It'll actually, instead of being a Blackboard test, you will go to Blackboard and access WebAssign to do the test, but it will actually be posted on the WebAssign. And you will have a flexible time to do the test. We will not have class this Wednesday. The test will actually be available on Thursday, and you will have till 11 p.m. on Saturday evening to have completed the test. So Wednesday you can use as a flexible day if you want to rest, get some extra sleep, or you know, at first I thought, well, I'll just have everybody take the test during our class period. But with technology and all that, that's probably not the best thing. And I decided to do something I did over the summer, which was to allow you a window of time to take the test. And so I think it'll be very flexible. And of course, you're used to your WebAssign homework and your quizzes. So the format will be the same. So hopefully that will make you feel good. I certainly would be happy for that if I were taking Professor Ron's class. Now, today what we're going to do is talk about work, but I did have an example that a couple of you asked about in the shell method. So what I want to do is go ahead and say something about it as a comparison method. So let me share my screen. And then of course we'll go to the work applications. Now, the question that I had, and again, WebAssign is really, when you compare it to everything out there, it is the best homework computer algebra system in existence. It was built at North Carolina State, my home state, at my arch rival school, the NC State. Of course, the University of North Carolina, then the rivalry was a lot more than it is now. Well, I don't know, maybe the students would disagree with me, but they really perfected the system. And the nice thing about it is that you get such a wide variety of formats of questions. And the one question, you all are going to say, well, this is exactly what you said, Professor Ron. You have a setup where you are given this region, and it's in the shell method. So what they're asking you to do is to revolve this region about the x-axis and then compute the volume of the solid of revolution. Now, of course, if you look at this and you think, oh, well, this would be perfect for the disk method, basically because you just have an upper curve and a lower curve. The region touches the axis of revolution. So that would be the easiest way to do it. And the way, for instance, if you're taking an exam, a test with Professor Ron, and it says compute the volume of the solid of revolution, you use whichever method you want. I mean, I would have no way of knowing which method you utilized. I mean, I'm just asking you to utilize a method to actually work the problem. Now, there may be problems that require a method, a specific method, like the volume of the torus, because the integrals are ones that you can actually do. And so what students are asking about is that it seems a little bit complicated. So you work this problem with the disk method just to see how easy it is. But what I wanted to do was give you an idea about the shell method. Notice with the shell method, all of the rectangles have to be parallel to the axis of revolution. And what I did is I blew this up. I mean, the scale is pretty horrible, but in the WebAssign, it's nice and trim and it's all nice and beautiful digitally produced, but I wanted to make everything a little bit bigger. So we've got this chunk here, which is basically a rectangle. And when we revolve it, we just get a disk. So if we wanted to use the shell method for that, we can just kind of cheat and do that one, with basic geometry. And the other one would be up here, again, because with the shell method, the height of the strip, so to speak, the H that we usually call this would be different. So notice with the first, I'll call this, let me just call this 2, and I'll call this 1. For 1, we see that the Y runs from 0 to 1/8. So for 1, we can just go ahead and do this. And notice we have a delta X here, or a width. We can really cheat with this, width equal 1. And so if we think about just revolving this piece around, we form a disk. So notice the radius of the disk is 1/8. So we could say this distance is 1/8. So we would say disk volume, I mean, we're just cheating to do this because it's so easy, would be pi r squared times the width. So we get pi r squared 1/8 times 1. How easy is that? That you don't even need me for this. This is general math. So we get what? 64 downstairs. So pi over 64. So you're thinking, well, you know, the shell method makes this look so difficult, but there's really nothing to do here. And again, how you interpret things, ladies and gentlemen, is up to you. There's no one interpretation that's good or bad. All interpretations are good if they lead you to the correct answer. Now, for this part for 2, again, I appreciate your questions because they give me ideas for warm-ups and things that you may be pondering. So notice here, the variable, and like I say, in the WebAssign, they wrote these as decimals. But if you have a decimal, that's exact. Again, any number you get in a problem is exact. But I wrote them as fractions because fractions to me are easier to work with. So notice we have y between 1/8 and 1/7. So that would be the interval of integration. Now, notice we pick a y here, and then we run over here and say, what's the length of this strip? Well, notice the distance out to here is 7, and then we go 1 over, well, and of course, this actual curve here, you're thinking I'm just having you make it up, is y equal 1 over x. All right, that's the curve. I guess you would really need to know that curve. But now, since we're dealing with the independent variable y, we would see now that we would just interchange and write x in terms of y, just like we do if we change to the independent variable y. So now this would imply that the length of the strip, in this case, would be 1 over y. That is, looking at this, you know, looking at as the right minus the left would be 1 over y minus 7. This distance here is 7, which is no man's land, and the distance from here to here is 1 over y. So this is 1 over y minus 7. So again, if you like, you can think of it this way, where you put in the y, and the point here is 1 over y. And so the distance from here to here would be 1 over y minus 7. So that's another way of looking at it. Now, again, we pick the y here, so the distance to the axis of revolution, p, is just what? Y. So this is distance to axis of revolution, like we do with surface area. So you can see when you do the disk method with this, you're gonna say, wow, I would never do this. But what I want to do for this particular problem is just give you an example. And let me check here. Where's the? resolution, here we go. Clean this up a little bit. Let me move this up. There we go. Good old technology here. Let me move this over here. There we go. All these things on the screen, boy, it's like juggling. You know, we've got to become better at this, or I do maybe. You all are already pretty good at it. So now we can see that with the shell method, we can now revolve this part and get its volume. But again, I want you as an extra, let me just remind you, solve with disk method. And then you'll just kind of laugh at this and think, yeah, I'll never do this again like this. But I want you to get some practice with this method. So this is not half bad. So now for this part, again, we've got the volume of the first part. So let's not forget about that. So the volume for the second part. So disk volume, so I'll just put volume here. And I'll write a volume of 2. This will be 2 pi. And then we integrate from 1/8 to 1/7. And then we have, in this case, the distance to the axis of revolution, and then the length of the strip. Okay, so again, this is much more complicated than the disk method. We have 1/x and we'd square it and get x to the -2, and how easy is that? So again, this is the quickest way to do it. But I looked at this problem and I know the student was having trouble with the application of the shell method, and this is important. So now this will be 2 pi, 1/8 to 1/7. And then when we distribute, we'll get a 1 minus a 7y. The y over y just giving us a 1. So again, the only thing that's hard about this will be the fractions. So this will be 2 pi. And when we integrate here, we get y minus 7/2 y squared, evaluated from 1/8 to 1/7. So now you're looking at this and saying, yeah, this is why I really don't want this problem. You know, the problem I worked last time with the cross-section method, you saw all the algebra with the fractions. I mean, you can't avoid it sometimes. So this will be 2 pi. So now we'll substitute 1/7. So we get 1/7 minus 7/2. And now, of course, this will be 1/7, so we get 1 over 7 squared. And now here we substitute 1/8, and then minus 7/2 times 1 over 8 squared. So you're thinking, yeah, this is like a pre-calculus problem when you're clearing denominators and getting common denominators. So we're going back to that class, which we often find ourselves. So now we've got 2 pi. Now, if you will, let's go ahead and put the easy stuff together. We have a 1/7 minus a 1/8, and then we'll get a common denominator. And notice here, one of the 7's absorbed. So we just get minus 1 over 2 times 7. And I'm leaving these factored so you can easily see the common denominator. And then, of course, here, notice we have a minus minus. So we get a plus, and we have a 7, and we have a 2 times an 8 times an 8. So I guess when you look at a problem like this, you're thinking, man, is this what I have to live with? And sometimes we do. But now if you were tutoring someone, they'd say, well, what do I do now? And then you say, well, we need a common denominator. We need 2 copies of 8, a copy of 7, and a copy of 2. And then, of course, I think one of those 2's will absorb, but we have to write this for now. So I want you to see how to do this with the horrible numbers and get practice. So again, if we start over here, well, we need a 2, we need a 7, there's only one copy of 7, and we need 2 copies of 8. So now when we compare here, we got the 7, but we need 2 times a 64. And then we compare here, we have a 56 times a 2 because one of the 8's is gone. And then we compare here, the 14 we have, but we need the 8 times 8. So that's a 64. And then what do we have here? We've got the 2, 8, 8, but we don't have the, oh, we don't have the 7. So that'll be plus a 49. That's kind of odd. I didn't expect that. Okay, that looks good. So now when you tutor students, it's good to keep things factored like this so they don't get crazy with all the numbers. I know that's a technique I adopted when I was in graduate school as a TA. So now we've got what, 128. And here we've got what, 112, 100 plus 12 minus a 64 plus a 49. Looks like everything's going to go away. And then, well, now one of these 2's will absorb with that. Well, I'll do it in the next step. So now this 2 and this 2 will absorb. So we have pi. And so now here, if you look at this, let's see, that's going to be what, a 6, a 16. So 2 from 8 is 6, and then 1 from 2 is 1, so a 16. And so that takes care of these 2. And then we've got a 64. So let me write it this way so it'll be easier. Too hard to add that way. That's going to give us a 1. And then, of course, one of these 2's went away, and we have 7 times 8 times 8. So now, if we look at this, that gives us the negative 48. Always add the numbers that are easy to add. I mean, don't struggle with the hard ones unless you're just forced to. So that just gives us a 49 minus a 48. So that's a 1 over 7 times 8 times 8. So now this is that's the part 2. So right there. And so when we add, so I'll say total volume. So this is just an exercise in arithmetic, which is really all we've been doing from the first day. So we get what, pi, and I'll go ahead and write this as 8 times 8. Well, not 88. Put a little dot in between. Plus pi over 7 times 8 times 8. Okay, and so I guess this will actually work. And so now we can factor all of this. This is really odd looking, but I guess that's what WebAssign does when they generate these things. So we get pi over what? Let me do it this way. I'll factor this. And then I'll have the 8 times the 8 outside. And then, let's see, what's that going to leave us with? I'll write these as separate fractions and then a common denominator. So that'll be 1 plus 1/7. That's one way of looking at it. So when you multiply back through, you get this term, and then plus you get that term. It looks kind of weird, sorry. Pi over 8 times 8. Now get a common denominator of 7. And so this will be 7 plus 1. Sorry, let me move this up. So now you see the disk method's a lot easier. So pi, so 8 times 8, and that'll be 8 over 7. Now, of course, one of the 8's absorb upstairs and downstairs, so that'll give us pi over 8 times 7, which is pi over 56. So after doing this, I just wanted to show you, because I looked at this problem when the student asked about it, and I knew exactly what they were talking about. The arithmetic here is more tedious than if you use the disk method up here. And so I think this problem, like I said before, was basically generated to give you practice with the shell method. But here's what I'm saying. And I did a problem like this in the lecture notes that are posted on Blackboard, where I said it's always best to pick the best method or the easier method, because the shell method like this had lots of arithmetic, whereas the disk method would be less. So what I want you to realize is that sometimes the disk method can be just a walk in the park. But when you compare this to the actual disk method and all, we can see that that would be much easier. But again, I do want you to work through this and appreciate the fact that we can actually work this with the shell method. And it's important, you know, like I say, as you do the arithmetic here, you're just doing algebra. So factor things and work with it so that each step is clean and you can go back and check your work. A lot of times when I work problems in my own research and I'm working with variables and numbers, I always write things out very cleanly so I can go back and check my work. And even though there'll be times when I feel like I've maybe added more steps, the steps are easy to check. So again, I felt for the student when they asked about this, because I said that's going to be an ugly number, and we get pi over 56, which isn't something that's just going to roll off your tongue. So again, practice with the shell method, just like you practice with arc length and surface area, and know the method. So just realize that you have a choice on a test. If you're asked to compute a solid of revolution, the volume, then you can choose whichever method you like. But just realize that one method may produce an integral that you don't know how to do. And so you'd have to use the other method. So that's the part of the process that's the decision making, so to speak. Now, what I want to do is say a little bit about work. And all you engineers and physicists will love this. Just like, you know, when you take your physics, you talk about work and you talk about center of mass and all that stuff. And those are great topics for physics. So what I wanted to do was do some nice examples. And this, of course, none of this will be on the test. The test will stop with 7.4. So this will just be stuff that will be on the second test. Now, and also go through those practice tests. I have some old tests from last fall with this class, and there'll be great examples to prepare once you finish all of your WebAssign. Now, work is an interesting idea. And let's see here, let me adjust this a little bit. There we go. It's basically force applied over a distance. So work, we think of force applied over a distance. Now, of course, we can do, you know, this is kind of an intuitive feel when we think about this. Now, you know, you think of force times distance in your physics class, if you took a physics class as a high school student, and some of you are taking that, and then you'll probably be taking Professor Goins for university physics. What we're interested in this class, I'll just say, are variable forces. So we need calculus when forces vary. Now, what I want to do is talk about some work that we utilize when we deal with springs, and also work that's utilized in moving liquids. Those are very interesting problems. And of course, in your physics class, you'll do more work problems, but these make really good examples for a math class. So what we want to do when we think of force over a distance, we have, and this can be a Riemann sum argument, work will be integrated over some interval of integration, say a to b, and we'd have some variable force, f of x, times the infinitesimal distance. So this is force over a distance. And this is a summative process, we know. So this is the Riemann integral, as we've been doing from day one. So the idea is that when we do problems with work, we have to identify the force. So here's, I'll just say, strategy. If we work with springs or moving water, strategy, we must identify f of x relative to the problem. And the problems we will start with will be springs. And that will be what we call Hooke's law. So springs, these are fun. You'll like these. And you may have already discussed these in your physics class. For instance, Hooke's law. So we could say, let x denote the measurement of compression or stretching of a spring. And this would be in units of length. Maybe you compress a spring 2 centimeters or 1 inch, or stretch it 2 inches or whatever. And Hooke's law is easy. The force, not writing this as a vector equation, just as a scalar equation, will be kx, where x denotes the measurement of compression or stretching, and k is a spring constant. So we can figure this out based on some given information. So when we talk about Hooke's law, we have a very simple way to define or identify the force when we're dealing with obviously springs. And so let's do a couple of simple examples with this. These are from your WebAssign. Again, you'll like these. And these integrals are certainly, I would say, less difficult than the shell method or the arc length, which require a lot of algebra, but we tend to still get some arithmetic with constants and things that just kind of pop into the situation. So here's an example. We have a force of 450 newtons, stretches, so we'll have to do Newton centimeters here. Force stretches a spring. I don't know why WebAssign decided to mix up the units a little. Spring 30 centimeters. Compute the work to stretch the spring from 40 centimeters to 70 centimeters. Okay, so let's get a clean sheet of paper so we have some space. So there's our problem. So make sure everybody has that. A force of 450 newtons stretches the spring 30 centimeters, and we want the work to stretch the spring from 40 centimeters to 70. And I just need a little extra space so you can actually see it. So now, we have Hooke's law. So let's go ahead. That is, we have 450. Move this down just a little. There we go. 450. And we've got Kx. We've got 30 centimeters and K. So this is Hooke's law. F equal Kx. So of course, 45 equals 3K. And K will just be 45 divided by 3. And that'll give us what, 15? It's amazing how sometimes and of course you don't have to put units here. We will for the final answer. Of course your physics professor would yell at you if you didn't, but I'll be okay with that. Sometimes the arithmetic is very simple. So this implies that for this particular spring, the identified force will be 15x. So very simple. So now, thus, work, and what we want to do, and also given, we will let X run from what, 40 centimeters to 70. So we need the work to stretch from 40 to 70. So this is the interval of integration. Lots of you asked very specific questions, and I actually cover all the bases, but I want to make sure that you build some confidence. You have to really go out on a limb with these problems, just like you're doing a chemistry problem or a physics problem to get all the motion started. So now we'll have 40 to 70, so a very simple integral, force over the distance. So again, compared to the other integrals we've done, especially at the beginning of the class, this is really simple. So we're going to get 15 times the integral 40 to 70 of x dx. So this is just add 1 divided by the new power. So we get 15 times x squared over 2, evaluated 40 to 70. So now we can bring the 2 over, if you like, the 1/2, and just write 15 over 2. And so this will be, well, let's go ahead and use a little algebra here. 70 is 70 times 10, right? Because we don't want to work too hard. Kind of like that shell method that shouldn't have been. Like I say, you know, you are in charge when it comes to choosing the method. So don't, you know, you can make good choices. Now, notice here, when we square this, we're going to get 100. 10 squared is 100. So we can just go ahead and factor the 100 from each of these like I did in the previous problem. Factoring is never going to put you in a bad way. When you're finding least common denominators, factored numbers are easier to work with. That's called symbolic computation, which I teach my pre-calculus kids, much to their chagrin. They don't like to do it, but they have to learn how to do it for calculus. You see what we're doing now. And so now this will be a 49, 7 squared is a what, 49, and 4 squared is 16. So we're kind of, remember that before? I didn't want to do that difference before. I said, forget it, I'll do an easier one. So whatever, I guess I'm stuck with it now. So that'll be 2 into 100, that'll be 50. So 15 times 50. And so now that'll give us a 3. So this will give us what, a 33. So now, in order to actually do this in a way that would be easy, we can do what I've done here, and what I've thought about is we can go ahead and multiply this out and then break it up into pieces. So like you do when you multiply numbers that you learned in what, fourth grade or fifth grade. So you have 15, and so here we've got 3, so that's a 15 with a 1. So that'll be a 165 with a 0. So now we can break this up into pieces. What I normally do, and this is up to you, you can say, well, since this is the smaller number, I can write this as 10 plus 5. Make it a little bit easier. So multiplication by 10 is easy. That will be 1650 with an extra 0. And then a 5, that'll give us a 0, 5, 5. And then a 2, and then a 3. So we get 8250. So adding, that'll give us a 0, then a 5 and a 0. And then a 2 and a 5, that's a 7. An 8 and a 6 is a 4 with a 1. So this will give us 24,750 Newton centimeters. Now, lots of times my pre-cal students run into this problem too. Don't put, even though I may put a comma sometimes because, you know, we just used to commas, do not put commas in WebAssign. Do not approximate anything unless they ask for an approximation. If pi is in the answer, then you use your little palette and you put the pi in. If you approximate something on a test, WebAssign will kick it out. You know, so I'm telling you right now, the exact answer is the answer unless an approximation is requested. And if they request it, then they will tell you how to round. Okay, so you know, follow the formatting, follow the directions. It will make you better. Just remember, as I've said before, I've had 11 years of students in engineering, math, computer science, you name it. I've even taught business majors that went from engineering to business because they like math, but they didn't like engineering. They all were, you know, trained on WebAssign, and it is a good tool. And it is frustrating, but again, leave everything exact. Always follow the formatting. Now, the next question is another work problem with the springs. And it's just stated a little bit differently. So I want you to take these problems as good practice and preparation for what you have been doing. So now we have 8 joules. This just kind of changes it up a little bit. 8 joules, like when you look in your physics book and you see all those word problems and you're like, oh man, gotta start putting some thought to this. 8 joules of work are required to stretch a spring, 1/2 meter, 1/2 meter from its natural length. From its natural length. Okay, so that's a big given. That will give us information that we need to move the problem forward. Then it says find the work to stretch the spring an additional 2/5 meter. So this problem is written in an interesting way and more complicated than the last one. So but we still use Hooke's law, and we still use the definition of work with the Riemann integral. So, so now look, we have 8 joules, that's work, required to stretch a spring 1/2 meter from its natural length. Okay, so basically the natural length we just say is 0. There's no stretch or compression. So this implies that we start out with the natural length, which is no compression, and we stretch to 1/2 meter. And these were written in terms of decimals in the problem, and I wrote them as fractions because they're easier to work with. So again, these are all exact. Just because something is given as 0.5 does not mean that it's not exact, okay? There are different rules like of rounding and all in physics classes, but with the WebAssign, the numbers you're given in a problem are exact. So what I do is I usually write them as fractions, but they are exact. You treat them as an exact number. Don't overthink this. If you do, it will always confound you. So now we've got the interval of integration, and we got work, and we have work equals 8 joules. And we know that that'll be the integral from 0 to 1/2 of the variable force multiplied by the infinitesimal distance. But now, of course, here, the variable force is Hooke's law. So basically, this will allow us to solve for K. So we want to solve for K. So we use Hooke's law. So we get Kx dx. So this is important. This problem is written just very differently. So solve for K. So now, if we look at this, we have 8, and we can factor the K, it's a constant. So 0 to 1/2 x dx. So add 1, divide by the new power. So 8 equals K x squared over 2, 0 to 1/2. So very easy. All of our integrals have been straightforward, but there's been lots of arithmetic, like when you did Riemann sums in Cal 1, and you thought, well, the fun is over. Well, the fun was over when you hit limits, really, but everybody seems to think they know limits until you ask them to prove a limit by definition. So now, when we look at this, we have, if you like, we've got 8 equals K over 2, and we just substitute. So we have what? 1/2 squared minus 0 squared. So now, if you like, we can go ahead, we could cross multiply if you want to just leave everything alone. I guess we'll just leave it alone. It's really not going to make any difference. And so now this will just give us a 1/4. So we get 8 is equal to K divided by 8, 2 times 4. So K is 64. And again, don't worry about the units. We just need the magnitude. And then again, you can easily figure out what the units are, but that's really not what's the focus here. Again, don't say anything to your physics professor. They understand you got to compute math. Physics professors at the college are always know my students. If they've had through Cal 2 and some through Cal 3 when they take physics, they said, you've had Professor Ron, and they said, exactly. They said, yeah, because you can do your math. But again, the student did the work. I just showed them some techniques and they took my advice. So you own your work, you make it happen. I don't make it happen. I just give you some advice and I say, work hard and try this and you're going to get better. But at the end of the day, you make it happen. You earn the grade, you acquire the knowledge, and you are the expert. Now we see, find the work to stretch the spring an additional 2/5 meters. So we're at 1/2. So 1/2 plus 2/5. Let's get a common denominator of 2 times 5. So that'll be a 5. And then we need a 2. So that'll be a 2 times 2 or a 4. So that'll give us 9/10. So this will imply that our interval of integration will start at 1/2 and end at the new 9/10. So 1/2 x 9/10. So like I said, the way this problem is actually written, it's a little bit confusing. Well, it's not confusing, but it's more difficult than the previous one where they just give you everything on a silver platter. So now this is the new interval of integration. So we want the work to stretch an additional 2/5 meters. So we just make the numbers user friendly. So now we get work, and we know everything. So we have 1/2 to 9/10. And then of course, we have our kx. So here we can just go ahead and say, well, what's Hooke's law? This is just kx, or 64x. So now when we integrate, we get 64x dx. So again, a very simple integral, a very doable integral. I'm gonna get a little more light on it. You know, this document cam does everything. I don't think it'll make me a cup of coffee, but it'll do everything else. So now let's work this. So we have 64 integral 1/2 9/10 x dx. So add 1, divide by the new power. So we get x squared over 2 1/2 to 9/10. And so now when we divide the 64 by 2, that gives us a 32. So that's an easy number. And we get 9/10 squared minus 1/2 squared. Now at this point, we can again get a common denominator. So we get 32. So this will give us these are easy numbers, so we don't always have to factor. This is a 81/100 minus a 1/4. So again, WebAssign really was good to us and gave us simple numbers. Let's just go ahead and get a common denominator of 100, and we're good to go. So 32. So we get 81, and then 4 times what, 25? Well, 4 times 25 is 100, so we put a 25 here. Yeah. So now we have 32 over 100. And let's see, that'll give us a 6 and a 56. That looks good. So now, if you will, we can go ahead and divide what by 4. That'll be an 8 over a 25 and a 56. And then, of course, 56 is just 7 times 8, so there are no common factors of 5 in that, so we're kind of stuck with this. So that'll be an 8 and then a 4. So 448 over 25. And in this case, again, this is work, so this is joules. Those are the units we started with. Again, the WebAssign is going to put the units by the problem. So the only thing you're worried about is computing is the number. So again, in the physics class, your professor holds you to units and things, and will, you know, sometimes when students decide to use whatever variable they like, that's fine, but WebAssign requires that you actually use their variables in a problem, especially if the answer is written in terms of algebraic objects other than numbers. So again, just be sure WebAssign will always give you the units to the side of the box. You just have to fill in the actual magnitude, so to speak. So again, this problem albeit simple for computation, is a really good problem, really actually a physics problem, where we just basically utilize the given to find the K, to write the Hooke's law for the variable force, and then do a computation to compute additional work required. So again, this just requires a little bit more work, but again, the computations are very straightforward. I think these problems are fun. I can remember as a kid at Carolina doing these in a physics class and even in math, and I enjoyed these. I felt more, that's when I figured out that I was more of a math brain. I liked the lab, but I don't think I was a mad scientist. And I'm sure many of my lab TAs were glad when I had not burned up the lab before the lab period was over. So now what I want to do, and this is another example, you know, we live near a lot of water, and liquids are moved all the time. So what we want to do is, you know, you think as engineers, you think about the chemical engineers that work at LyondellBasell. And I've taken groups of kids out there before. We actually had a math and engineering club. We don't have one anymore because no one has time for it. But there was a day when students actually enjoyed the club, and you have all kinds of work going on, and work with chemical reactions and physical work in terms of the calculus in both cases. But a lot of you will probably, some of you will entertain the idea of moving into the chemical engineering field, and you will certainly be moving liquids, but you'll be more interested in the properties of the liquids, and then using the physics to get those liquids where they need to be in order to make certain products. But the good thing about being an engineer in this area is that you don't have to move to another country. There are plenty of engineering jobs in this area. Now, when I talk about moving liquids, we always need to have what we call a weight density. That is, we need to compute a volume, and then what we need to do is make sure that we have a distance. So we're going to compute a volume and then hit that with a weight density. So we have the variable force and then multiply by the distance. So again, this will still be force over a distance, but just a little bit different approach to mark the fact that instead of a spring, we've got a liquid, and so our variable force will of necessity vary. So we have a rectangular, here's another WebAssign, rectangular tank. Rectangular tank with base (4 feet by 5 feet) and height 4 feet. So we just basically have a box, and the tank is full of water. The tank is full of water. And I'll show you a little technique to do these. Now, for this particular problem, we're going to be using English units. Sometimes we'll use English, sometimes WebAssign will use the metric system. So here, the weight density of water is 62.4 pounds per cubic foot. So this is a very popular quantity that if you took physics, you know, if you've ever taken physics, you've seen this number before. It's very popular. It ends up in many tables. So how much work is done in pumping water out over the top edge? Out over the top edge in order to let's do this. We'll do in order to empty A, all of the tank, and B, half of the tank. So when you look at these kinds of problems, again, the sketch is kind of like doing a shell method or a disk method, just kind of giving you some orientation as to how things fit together. It's not always required, but I think it's a good tool just to kind of organize your thoughts, like doing a word problem in college algebra. So what I want to do, and this is where you get to be very flexible. We can draw, let's go ahead and draw a box. And again, it doesn't have to be perfect. Let's just draw a box so we can look at a picture of what's going on. Again, then we can add an axis where we like to make the problem numeric for us. So just doing the edges here, just like we would do in Calculus 3. We were doing a parallelepiped. Calculus 3 is a very, very elegant class. And everyone says, oh, it's simpler than the others. No, it isn't. I find that I learned correctly as an undergraduate. My Calculus 3 professor said, this is the hardest class, but you'll think it's easy because you've done all the work in Cal 1 and Cal 2. But I agree with her. So now, if you will, we can go ahead and use some of these dimensions here. Like I'll put, say, 5 feet here. Doesn't matter. 5 feet. And then a 4-foot edge. And then a 4-foot height. Now, this is where you can be flexible here. We'll just go ahead and put an axis right here, a y-axis, anywhere you want. And we'll call this y, and you have a 0 here, and you have a 4 here just by definition of the dimensions. So the idea is what we want to do is think about an infinitesimal slab. So first, I'll do this here. Once we call this particular axis a letter, we'll let y live between 0 and 4. And then we're gonna start with A, so the tank is full. So we're gonna take a y between 0 and 4. And like before, we would draw a rectangle. Now you can just sketch in a little slab. You don't have to do this, but again, just sketch a little slab of thickness delta y. Just so you can see that we're going to be moving these slabs of water. And we'll use the integral to add them. So we've got this, if you like, you can put a little shading there if you want. You don't have to. So we have a slab of thickness delta y. Now, we'll figure out the actual volume of this and then hit it with the weight density. But notice now, we have to move this slab a given distance. We have to move to the top edge of the tank. So here, D, this is like doing the shell method, is 4 minus y. That is, this slab will have to move a distance 4 minus y to make it to the top of the tank. So again, it's like the distance to the axis of revolution in the surface area in 7.4 or in the shell method in 7.3. So all these items are starting to repeat. And so now this is a very simple setup here, which is nice. We've got the 5 and the 4. So the volume of the slab, we'll call that delta V, will simply be 5 times 4 times its thickness, delta Y. So this should appeal to your physics and engineering side. These problems are fun. They're all fun, but this is where students actually start to like calculus too. And then of course we don't do it anymore and do stuff they don't like to do. So now when we think of the force, we think of absorbing the cubic dimension here. So now this will imply that the force exerted by the slab will be rho, and if you like, just go ahead and say 20 rho delta Y, where rho is 62.4. We'll write it as rho, and then when we do the computation, we rewrite it in terms of its actual value. And so now what's the work? And of course we could use the interval, the partition and eyes and all of that, but I don't do that. We have enough information here without having to go back to the Riemann sum. That's really reinventing the wheel, and you don't have time for that. So now we can say the work to move this slab that distance will now be 20 rho, and we'll multiply 4 minus y delta Y. So again, this is force over a distance. So when moving the water, we simply have to compute the volume of the slab of water. We have to then notate the distance the slab must move and then hit it with the weight density. Now this is more complicated than the spring problems that we did with Hooke's law. But again, this is all motivated with the dimensional analysis. You know, we're not getting crazy with writing down a bunch of dimensions here, but we keep the dimensions in the back of our brain to note that certain dimensions need to absorb so that we can actually end up with a force, and then we have force over the infinitesimal distance. That is, we chop this up and then we add it with the actual Riemann sum. So the thing is, we work this like this is just a standard force, not a variable force, force over a distance. But we know that delta Y there is telling us that it's not. And we clearly see here that with the delta Y, we do have a varying situation. So again, just remember, slab volume multiplied by the weight density, and then force over a distance. So now this implies that the work will be 0 to 4. And we just fill this in, 20 rho 4 minus y. And of course, the delta y becomes dy, just like with all the methods we've done before. So this is easy. We can dress this up, add 1 divided by the new power. So now work will be 20 rho. Now we have a 4 minus y, so the chain rule, we have a negative 1 here when we differentiate with respect to y. So let's put in the negative dy and then pay for it to make this table ready. So now, of course, we can add 1 divided by the new power, and that's so much easier. So this is table ready. So we have negative 20 rho, add 1, so we get 4 minus y, add 1 to get a square, divide by the new power, which is 2, and evaluate between 0 and 4. So the same song and dance. These integrals are usually not very hard, ladies and gentlemen. They're very straightforward. We just have to keep track of all the arithmetic and the setup, which is usually more complicated, but every part is important. So now here we've got the 2 into the 20, that'll give us a negative 10. And while we're at it, rho is just 62.4. And now when we evaluate, when we replace with the 4, we get 4 minus 4, so we get 0 squared. And then, of course, when we replace with 0, we just get 4 squared. So now, if you will, we've got a negative 10 times a 62.4 times the negative 16. Now, of course, with this type of problem, we can use the 10. We don't even have to get creative to get rid of the decimal. And then I think what I wrote here is I just broke up the 16. So the negative times the negative will be the positive. And then that goes away, and then just move this decimal 1. So this will be what? 6, 2, 4. And then we can write the 16 as 10 plus 6. So again, the negatives absorb, hit the 62.4 with the 10 to give us this. And so that's all clean. And so now multiplication by 10 is easy, 6,240. And then hit this with a 6. So this will be a 4, and then a 2, that's a 14, and then a 1, 37. So let's add these. We get a 4, and then a 4 plus a 4. That'll give us an 8, and then a 7 plus a 2, a 9, and then a 9. So in this case, we get 9,984 foot-pounds. And those are English units. Again, I grew up with English units. I was told when I was a kid that the metric system would take over, and that we would never use inches and pounds ever again. That we were done with this. Learn the metric system. Well, it didn't happen. What do we use today? We use the metric system, but we're still using the English system of weights and measures. I mean, it's weird. There was this mad dash to educate everybody about the metric system, and then of course it never happened. So I guess it just really depends where you live. You go to Europe and everything's metric. Now, let's finish the problem. We want to now do the B part. So this is the A part. Now, basically what we want to do is we want to pump out half of the water. So now what we want to do is consider if we pump out half of the water, then that's just basically half of the tank. And what's our new interval of integration? Well, it's going to be 2 to 4. So for half of the tank, this is equivalent to integrating y from 2 to 4. So we're only going to move out water in this region to empty half of the tank. The tank is full, and we want to only empty half of it. But the thing is that with this, what we want to say here is write new interval of integration. New interval of integration. We don't have to start over. By all means, we don't have to start over. We just now know that we only have to move out half of the contents. So this just means that we set up the integral as we had before, but we change the limits. So this implies that we have work equals the integral 0 to 4, 2 to 4, but the only change I left out, 2 to 4, and I'll just go ahead and write this 20 rho 4 minus y dy. Now, if you like, we can go ahead and move to a step that's simpler. We already have done all of the work, so we can just jump to this point here and change the limits. So we already have the work, so we'll just go to here. So we get negative 20 rho 4 minus y squared over 2 to the 4. So again, think of the fact that we're only emptying half of the tank, and that doesn't require a complete reworking of the problem. That's the beauty of the calculus here. That's really what lessens our work. So now we can move here and just copy this. So we have negative 10 times 62.4. And now we have new limits. The 4 gives us the 0 squared, that's the same. But now when we substitute the 2, we get the 4 minus 2. So that's going to give us a 2 squared, which gives us a 4. So I'll write 2 squared. So this will be negative 10, 62.4 times a negative 4. And let me get another sheet here so you can see my work. I'm close to the bottom of the sheet. Let me move my Wacom pen. And so now we'll do the same thing we did before. Just go ahead and absorb the negatives here. Let me move that over. Absorb the negatives, and then hit this with a 10. So this gives us 6, 2, 4 times a 4. Oh boy, that was a walk in the park. So now we have a 4. So that's a 16, a 1, a 9, and then a 24. And this will be foot-pounds. So the beauty of this problem is that we really only have to work it once. But if we're only going to empty half of the tank, then that will change the limits of integration from 0 to 4 to 2 to 4. And that's all the adjustment you have to do. That's where the beauty of the calculus is our friend. You don't have to completely rework the problem. And so that's an important concept, okay? So this is a very nice problem and a very good problem to start. That is, this is a good place to start where you've got some basic geometry, straightforward geometry, good recipes. Do this every time so you can write this. If you have a little sketch, just like doing the shell method, it does help to organize your work, okay? So let's look at another example. I thought you would like these problems. They're a little bit more entertaining and maybe not so dry, because you're actually computing a physical quantity. So just think of it this way. When the calculus was discovered, and it was discovered, I mean, Leibniz and Newton are credited with its invention, but I think they just found it. Things are already out there. We invent, discover, whatever you want to call it. But it is so profound that we continue to use it to this day. So let's look at another example. Say we have a cylindrical tank. Let's change the geometry of the tank. A cylindrical tank, or I'll just say this water tank. We'll use the passing T, we say water. It's not water, it's water. We just don't know how to pronounce English. And English is actually quite difficult to pronounce. And so I apologize to all of our international friends and all of you that speak 2 languages. I try to be very careful with my English, but I'm sure there are times when I focus on a syllable and pronounce the word incorrectly, but please forgive me for that. So a cylindrical water tank, 4 meters high, with radius of 2 meters. Is buried so that the top of the tank, like think of like a Coke can or something, that the top of the tank is 1 meter below ground level. So again, you can think of gasoline when tanks that are buried vertically. Okay, so the axis is vertical. That's often a way that happens where you have gas stations and all where you get gas for your vehicles. And we want to compute the work to pump a full tank of water to ground level. Compute the work to pump a full tank of water to ground level. Now, again, WebAssign is now wanting you to use metric system. So they're going to give you the rho to be 9,800 newtons per meter cubed. So again, just remember when you're doing these problems, if they don't ask for an approximation, you can even type products in your answer. WebAssign will usually say fine. If you don't want to multiply everything out, WebAssign will read it, and in a lot of these cases, it will accept it. So just make sure that you take everything as exact. And if there is no allusion to any approximation, then you give an exact answer. No rounding, no nothing, just as it should be. And if it means it has a pi in it, then you use the pi from the palette, okay? Don't do 3.1416 or whatever. That's wrong. Anytime you elect to approximate and the problem does not specify that, it will be marked wrong. So don't do it. Do not do it. So what we have here, if you like, is let's just go ahead and draw a tank vertically situated, and then we can add an axis. Again, we're not Rembrandt here. We're just doing a math problem. So, you know, we can cheat a little perspective drawing. And these are, you know, right cylinders. You know, they're not like, you know, slanted. You know, we like the rulings are parallel to a given axis. So here's our tank, and I'll just write here ground level or ground. So what's usually simplest is to run an axis right through the center of the cylinder, just like we did the sphere before. So you are at liberty to use whatever you like, but simple is best. So this is Y, and if you like, you go ahead and run over this way. This is 0. This is 4, because we know that we have a height of 4 meters. And all the way up here is 5, because we know that the tank, the top of the tank is 1 meter below the ground level. So at first, at least for the water in the tank, we see that Y lives between 0 and 4. And another thing that we're given is that we have a radius of 2. So the distance from here to here is 2. Okay, so this geometry is not complicated, but it's different from the last problem. So when we think about this, we've chosen this. So let's just take a Y. Let's take a Y on the Y-axis and draw a slab of water. So we just need a little disc. So put your little horizontal lines and draw another disc. Again, you don't have to do this. It just kind of gives you some perspective. And the WebAssign always tries to give you a little diagram or something that makes it a little bit more real for you, but you don't have to do this. This just organizes your thoughts, and most students tend to like it. So now again, this is also 2 here. So we have the radius with this cylinder that is fixed. So that makes our life a lot easier. So this implies, if we look at this now just to kind of finish it off, from this y all the way up to the top to the ground level, we'll say distance is what? We have 5 minus y. So the tank runs up 0 to 4 meters, but then we have an additional meter to ground level. So the distance this slab will have to move, well, to the top of the tank, and then the additional of a pipe or something, small pipe or whatever. We doesn't magically get up there, but it certainly won't be running through the cylinder at that time. It'll be in like a small water pipe. So now when we look at this, we're thinking, what's the volume? Well, this was like the very first problem with the shell method. This is a circular disc. So we have pi r squared, so pi 2 squared times delta y. So we get 4 pi delta y. All of these problems, when you're working these, work them out like I'm doing them. I'm giving you techniques. If you don't do this, you will make mistakes. You'll make mistakes even when you're very careful. But if you don't approach the problems this way, you will not have the success that you want. So you need to be very careful at this time and work through things just like I have in lecture. And the ones that you see in the test, the lecture notes that I have handwritten that are on Blackboard also give you some help along those lines. So now the force will just be our weight density. So that's going to be 4 pi times the rho weight density delta y. So that will absorb the cubic meters. And so the work will now be the force over the distance. And so we've got this force here times the distance. So we've got what? 4 pi rho. I'll put the delta y over here. Here's my distance, 5 minus y, delta y. So now, like in the previous problem, this infinitesimal is tied up with the force, and the distance the slab moves is right there. So everything works out well. So again, we remind ourselves that, again, y lives here. So work, in this case, will be the integral from 0 to 4. So this will be a 4 pi rho, same kind of integral we had before, times 5 minus y dy. So again, you think, well, that's easy. I'll just jump to this. Always set up the problem. That way you have something to check. If you have a typo, you can find it. I mean, like I say, it's the worst thing in the world to have a bunch of arithmetic on a page and have to say, well, I've checked it twice, 3 times, I can't find it. And then you just pretty much have to start over. That happens, unfortunately, but at least you have something to check. So now what we can do is make this table ready. We've got the negative 1 here with the differential. So this will give us 0 to 4. And I'll leave a little more room out here. So we'll have a 4 pi rho, and we'll have a 5 minus y and a negative dy to make it table ready. And then, of course, pay for it, because we always have to do that using the linearity of the integral. So this will be negative 4 pi, and this will give us 9800 integral. Oh, well, we're ready. Add 1, divide by the new power. So this will be 5 minus y, quantity squared, over 2, 0 to 4. So now, if you will, the 2 will absorb here. And I think, or actually to make it a little bit easier, we can just go ahead and absorb it there. And let's see here. So we'll say negative 2 pi 9800. And then we'll substitute 4. So this will be a 5 minus a 4 quantity squared minus, and now substitute the 0, and this will give us a 5 squared. Again, the 2 we absorbed here to give us the negative, okay? So we've taken care of the 2, we didn't forget it. So this will be a negative 2 pi 9800. And now we have a 1 squared, and we have a 25. So we have a 1 minus a 25. So this will give us a negative 2 pi 9800 times a negative 24. So the negatives will absorb. Now at this point, and this is one thing you can do, hopefully to make the work a little bit simpler. I would suggest at this point, let's see here, I've got the, let's see here, where did I get that? We got the 4. Just want to make sure this is going to work the way I want it to. So we have a pi. Yeah, we can go ahead and run the 2 in there or leave it out. Let's do this. The negatives absorb. And then here, let's do this. Let's make this into a, I can break that up. I'll do it this way. So let's make that into a 48. So we have a 24 times a 2 and a pi. And then we have a 9800. Okay. So with that, let's bring the pi over here to get it out of the way. And we're going to do 9800. And I'll just write this as 40 plus 8. Since that's pretty simple. That'll make the arithmetic pretty easy. We can do that. So this will give us pi. So we'll first, we'll multiply by 4, and then I'll add the 0. So we get 0, 0, then a 4, that'll be a 2, and then carry your 3, that'll be a 39, with an additional 0. So 392,000 plus, and now we've got an 8 here, so that'll be 0, 0, and then 8 times an 8, that'll be a 4, with a 6, so that'll give us a 78. Again, at this point, just kind of decide which is the easiest way to multiply these. It's your choice. Again, it doesn't matter. The result will be the same. So now we have a pi. So let's start at the end here. We have a 0, and then we have a 0, and then we have a 4 and a 0, and then we have an 8 and a 2, that'll be a 0, with a 1. So that will be a 17, and then a 1 and a 4. So we get 470,400 times the pi. So this will be 470,400 pi. And in this case, we've got newtons and meters, so Newton meters. So again, when you start worrying about the arithmetic here, just look at this as a means to say, okay, well, just like with the last problem, and as you look at the numbers, negotiate them in a way so that the arithmetic is simple, and then you can easily go back and check everything. But again, exact answer. We need a pi here, not an approximation. Again, this is pretty much a paraphrasing of the Webasine problem. In no place do they say approximate. So all of your answers are assumed to be exact. You take that for anything that we do in this class. All of the answers or responses are given as exact unless otherwise requested. So that's kind of a fun problem. But just remember here, when we compare this to the last problem, the only difference is the geometry of the tank. We had a box before, now we have a cylinder. So you can think of all the tank companies that exist. Other tanks could be spheres, and those are popular shapes for tanks, and other popular shapes are cones. So let's look at one of those. Now I wanted to spend a little bit more time on the work just to give you some practice setting up the integrals, because I think it's good practice. Now the next example looks like this. We have a little bit more flexibility, and then the next application we'll do will be center of mass, and then we'll start looking at some review of some integration techniques. So it'll be good stuff. So now let's see here. What do I want to do? Yeah, this is a good one. We have an open tank. An open tank has the shape of a right circular cone. Again, we always do right circular cones. We don't want them to be slanted or anything. This is our geometry that we depend on. You do the same, like I say, in Calculus 3. The tank is 8 feet across, 8 feet across at the top. This is just a good geometry exercise, and 6 feet high. Water is pumped in through the bottom of the tank. And again, we're given rho is equal to 62.4 pounds per cubic foot. Now, here's the first question that we want, and I'll probably let you do the second one. It says, work to fill the tank to a depth of 5 feet. Compute work to fill the tank to a depth of 5 feet. Now, again, when you think about these problems, it's like, okay, well, I need a volume of some kind of slab, and then I need a distance that slab has to move, and that means, well, I need an interval of integration. And so in order to do that, I've got to take into account the geometry of the actual tank. And so the problems that we do here will be based on geometries that you know. So let's go ahead and look at a picture of the tank. We'll think of a cone that's situated vertically. Now go ahead and think about the center of the cone here, and then kind of eyeball where the apex will be, and then you can draw edges like this. Okay. Now, just like with the cylinder, we're going to think of an axis that goes right through the axis of the cone. So we're thinking about a vertical axis here, a y-axis, so to speak. And we'll just kind of continue that way. If you want to think of an X, we're not going to use it, but just like with the last problem. Now, what are we given? We have 8 feet across the top. So we know that we have 4 at that radial point. And also, we'll have a 6 here. And at the very top, this distance will rise to 6. So that's important in the sense that we had the bottom of the tank and then the height of the tank at 6. Now, again, we want to compute the work to fill the tank to a depth of 5 feet. So water will be entering here and we want to fill to 5 feet. So this implies that Y will live between Y and 5. So remind yourself, fill tank to 5 feet. So that gives us that for free. Now what we want to do is utilize maybe some geometry to kind of figure out, we look at this problem and we say, well, the radii in this case aren't going to be constant because they're going to vary as we move down, they're going to get smaller. So first, what we're going to do is we're going to take a Y here, some distance. And then if you like, this distance here, we can just call R for radius. Let's call this R. So take Y between, I've always been doing this, but here I'm making it a little bit more important, between 0 and 5. And again, we have a right triangle there. Notate this distance. So again, we have a distance of 6, we have a distance of Y, this distance of R, and this distance of 4. So this will allow us to write this radius in terms of Y, and so we'll know that it varies. So use similar triangles. This is a hard theorem to prove. The law of similar triangles is no slouch to prove. Ask some of my former honor students who had to do it. They thought it would be easy, and it turned out to be anything but that. And you can't use the law of sines to do it because it's a circular argument. But they tried. So now let's just see how we can do this. We can say R over Y is to 4 over 6. So this if and only if, this implies R over Y, ratio of corresponding distances, 4 over 6. So the shorter to the longer, shorter to the longer. Radius, radius, corresponding heights, heights. So if and only if, this is R over Y equals what? 2/3, since we can factor a 2 from each of those, and now we can cross multiply. So R equals 2/3 Y. So now we see that this problem is a little bit more complicated than the last one because the geometry is more complicated. Since we have a tank that's in the shape of a cone, a right circular cone, the radii will necessarily vary. And so we can't just say, okay, it's going to be this for all of them. So now, if you like, let's go ahead and put in a slab. You don't have to do this. This is just kind of a visual treatment of it. So we'll put in a slab here. So here's our slab of thickness delta Y. And now, again, we want to fill, we've got to figure out in this case, you know, what are we doing? We're filling the tank. Okay, so water, and this is where we have to think, this is very different from the last problem. Water is coming in here, and so slabs will move up. So we're thinking, you know, we think about this distance here, the distance that this moves is Y. So this is a very different problem. We think of moving the slab up into the tank because the water enters here. So let me remind you, water enters here. So we think of these slabs as moving up, and we know that from the given that the interval of integration will have to take us from 0 to 5. So as we pump water in, we move up the tank. And so the distance that the slab moves is different when we're trying to evacuate the tank as opposed to fill the tank. So just remember, we are filling the tank, filling tank from bottom, filling tank from the base. And so that gives us a D equal to Y. So that's a big difference here. So make a note of that. That makes this problem much more difficult than the last one. So now we can say, all right, well, let's go ahead. We've done all this work. Let's get the delta V. Again, this will be pi r squared times the thickness, because this is a circular slab. So we have 2/3 y squared times delta y. So that'll be a 4 over 9. So 4 pi over 9 y squared delta y. This practice will get you in good shape for reviewing all the other techniques, because this type of work makes you even sharper when you actually go back and review the arc length method in the surface area. This requires a little bit more logic, whereas the others, we just focus on the geometry and fill in a formula. Now, the force will be the volume here times the weight density. So this will be 4 pi over 9 rho y squared delta y. Now, if you will, we can do the work. So this implies the work for this particular slab will be the force times the distance. So this will be a 4 pi over 9 rho, and I'll write it separately, y squared times the y, and I'll just put the delta y on the end because it looks better that way. So now we'll just multiply this together. So this implies at this point that we get work equals our interval of integration, remember, is 0 to 5 because we're only filling to 5 feet. And we have 4 pi over 9 rho, and then y squared times y, which is y cubed dy. Now, again, the intervals that we normally get are not overly complicated, but we have to think about the logic of what's going on here. We're moving a slab of a given volume a particular distance. And since we're filling the tank from the base, the distance will be here. So instead of looking at from the top down, we're going from the bottom up. So now let's go ahead and factor this. We can go ahead and remove all of this stuff. So we get 4 pi over 9. And if you will, the rho is just 62.4. We have the integral 0 to 5 of y to the third dy. Now, boy, this is really easy. The payoff was the real simple integral. You know, since we're filling from the base, the distance is so much simpler. There's not a difference. The difference makes the integral more difficult. So we get 4 pi divided by 9, sum 62.4. Add 1, divide by the new power. And integrate from 0 to 5. And so now, if you will, the 4 and the 4 here, they absorb, and we're just left with pi over 9. So absorb, absorb. And then, of course, we will substitute 5 in for 4. So we get 5 to the 4th minus 0 to the 4th. Now, this is where we can utilize the power of the WebAssign. Now, notice this is just 25 times 25, so that's 625. So we get pi over 9, 62.4 times 625. So this gives us 625 pi over 9 times 62.4. Now, this is where if you were like, I'm done, I'm not going to do any more, this is an acceptable answer because all of the numbers are here, and WebAssign would read this as equivalent to another answer that is deemed correct. So if you're getting kind of weary and you got to this point on your test, WebAssign's going to mark it right. I mean, and of course, if they didn't, and I looked at it, I would mark it right. But normally, WebAssign won't have an issue with this. They don't necessarily consider this unsimplified, at least in the terms of numbers. So this would be in foot-pounds. Now, if you wanted to continue, we can use another technique that I've taught you. So for instance, if you wanted to move this forward to a different set of numbers, here's a little trick. So again, as long as you enter the exact numbers, WebAssign is fine. If they specify simplification, then fine, but they would not have an issue with this. So if you wanted to make this simpler, here's a technique that you could use that I think might be worthy. The only difference here is we have to break up the either the 625 or the 624, and you're thinking these numbers are so close, we could use a factoring identity. But here's a technique to do it. You can multiply and divide by 10. 625 pi over 90 times 624. And if you like, go ahead and pull this over. So this will be pi over 90. And we have 625. And then we can write, if you will. And I'll say this, every time you do this, just pick the number of your choice. We can do 600 plus 20 plus 4. That's just how you multiply numbers anyway. That's how you learn how to multiply numbers in the 5th grade or whenever you learn. So we have pi over 90. So we got the 2 zeros. We'll add those last. So we've got what, a 0. And then we have a 3. So that's a 15. And then a 1. So that's a 37, 0, 0. So 375000. And then here, this is not too bad. That'll be a 50 and a 12, right? So 12, yeah, that's right. And then let's see, 1 0. Let's see, so let me make sure I've got all the zeros here. 2 0, oh, 1 more 0. So here, you can do this in your head. 2 times 625, that'll be a 1250, add an extra 0. That's easy numbers there. And now for the very last one, that'll be, the 600 will be 2400. And of course, 4 times 25 is 100. So that should give us what, 2500. So those numbers weren't too bad. Again, the numbers are a little bit simpler here. And so pi over 90. So we'll add the last one. So 375000. And so we'll have a 0, a 0, and then a 5 and a 5 is another 0, and then a 2 and a 2, that'll be a 5, and then a 3. So that'll be 35000. So again, 0, 0, and we get a 2 5s, which is a 0, and then a 1, 5, and then let's see here. Oh, 1, sorry. Every time I have a typo, my brain says, Professor Ron, don't make a typo. Pi over 90. Now add these up from the rear. So we have 0, 0, 0. And then we have a 5 and a 5. So that's a 0 with a 1. So that will be 8, a 9, and then a 3. So if it bothered you to stop here, you can do this, and then we can make this look a little bit better. Notice we have a 10 in all of these, so we can absorb the 10 that made this without fractions or decimals. So this will be 3, 9, 0, 0, 0 pi over 9. So again, the 10 that we use to make the arithmetic easier, we can now absorb. And so we get this, and this of course will be foot-pounds. So this is the same technique I've been using to get a nice exact answer. If you don't want to leave it with this. But like I say, if you're starting to get weary and you're thinking, okay, well, I'm just going to leave it like this, type it exactly, WebAssign will give you a thumbs up. But if you want to go ahead and move it without the decimals, you can use this technique to get rid of them and then proceed like we've done before. The arithmetic's important because it's really what keeps a lot of students from moving to the next level. So it's nice to have some way to do the arithmetic that at least we can check. I mean, you can always go back and look to see what you've done. The most difficult thing for a computer to do is add and subtract. Multiplication is easy to do, but adding and subtracting is difficult. So now, let me just say one more thing. There is an additional part to the problem that says basically filling from 1 to 6, and that would just mean that you would change your integration interval from 1 to 6 like we did with the first problem. So that will be doable. I do want to make one comment about a problem, an extra problem that I want you to work on when you have time after you finish this test, because I know you've got to complete your arc length and area in 7.4. But I wanted to share with you a problem that I put in the lecture notes, and that's this one here. And it has the same technique, but I had a question about the torus volume that I did in lecture last week. And this reminded me of this problem, because remember in the torus problem, you actually utilize an even function integrated on a symmetric interval, which gives you 0. And then you had this nice Pythagorean integral that actually is just the area of a semicircle. And so I thought that was a good example when I was discussing this with the student. And then this reminded me of a problem that I have in the lecture notes, the handwritten lecture notes on Blackboard. And I just want you to look at this. Go ahead and write this down, then I want to kind of show you the solution. We just have a few minutes left, so I wanted to share this with you. So we've got a cylindrical tank of diameter 3 feet and length 4 feet, is carried on the back of a trunk and is used to fuel tractors. Now, what's different about this is that the axis is horizontal. It's not vertical, it's lying horizontally. The axis of the tank is horizontal. Then it says, the opening of the tractor tank is 5 feet above the tank on the truck. Find the work in pumping the entire contents of fuel tank into the tractor. So you got your truck riding through the farm, and you've got to fill up the tanks of the tractors, without having the tractor go all the way back to the maintenance building, and maybe to save some time. And so in this particular problem, we have a different weight density for the fuel. It's 42 pounds per cubic foot. So it's less dense than the water. So again, we're not stuck with water. We can you work at LyondellBasell, you can move around any liquid of any weight density. So I wanted to show you this, and you can find this in the lecture notes. This problem is done the same way. And I just wanted to summarize this as the last problem. Now, notice here, when we think of taking a cross section here, and this is what's important, we've got this tank that has a diameter of 3 feet, so that means it has a radius of 3/2. So when we think of this horizontal tank, again, that has length 4 feet, we think of taking a cross section right through the tank, and so it's circular, okay? And so in this particular case, we will see as we think, well, how did we do the last problems? We would choose an axis that was simple. So we take the axis to run right through, or the origin to run right through the center of the circle, okay? So we have this nice symmetric interval relative to y. And then, of course, we've got this nice circle, so the x's and the y's are interchangeable, so we can just set x equal to the square root of 9/4, which is 3/2 squared minus y squared. And then, just like you do many times in the cross-section problems, we're going to take a y in this interval and then figure out what the volume of the slab is. Well, remember, just like in the cross-section problems, we have to go all the way across, so we're going to get twice the radical. And then we have the width, delta y, and then we have the length of the tank, which is 4, in this case, 4 feet. So we get 2 times the radical times the delta y times the length. So the slab runs back across the length of the truck bed. And so our volume, again, is computed like we've done in previous problems. And now we can just simplify. The 4 times the 2 is 8, and then the force would just be the volume multiplied by the weight density. Okay? So we see that the problem is done the same way. We just have to now use the geometry that's given to us. And now, of course, the work, you think about this, and this is where it's a little bit harder. The tank is 5 feet above the top of the filling tank. So to 3/2, we add 5 and get 13/2. So this slab has to move all the way to the tractor tank. So again, this is what we've been doing. This would be 13/2 minus y. So the distance will be going up again. The upper minus the lower, because we are evacuating the contents of the tank as opposed to filling it like we did in the previous problem. And so now when we look at the work, we just simply have the force times the distance. So these problems are not difficult. Once you use the techniques I've taught you here, you're a professional, you can do any. But now you're thinking this is exactly like the torus problem. It's exactly the same. The mathematics works out exactly the same. So when you multiply here, we end up with a 13/2 times the square root, which is identifying half of the area of the circle of radius 3/2. And then, of course, we have in this case, a y times a radical, which makes this an odd function. Again, we've got the square and the first degree here. This is an odd function on a symmetric interval, 0. It's exactly the same as the torus volume. So I thank the student who asked me about this last night, because it gave me an idea for the conclusion of this. And so now we're done. That part is 0. And then we take half of the area of the circle or the area of the semicircle and put in all the numbers here. So at this point, it's academic. So basically, we have 26 rho pi times 9/4. And then if you like, you can clean this up and add the actual weight density, which is 42, and get this. Now, the idea that I did at this point is when I did my symbolic computation, I got to here and I thought, well, this is unfortunate. So what I did is I just wrote 39 as 40 minus 1. So this would be 40 times 63 minus 63, which will give you these simple numbers. And we get an exact calculation of 2,457 pi foot-pounds. So I put at the very bottom, nice example. Well, Professor Ron thinks every example is a nice example. And if you're in math and you don't think these are nice problems, then you're in the wrong course. The idea is that as a future engineer, this should be entertaining to you. This should be something you love to do. So now just think about this problem. You can go back to your notes and work through this and compare this to the problem we did with the torus volume. It's the same thing. It's just that we get at an integral that looks just like the integral we used when we employed the shell method for the volume. Doing this work problem, we get the same. So I think it's amazing how the techniques basically repeat themselves in what appear to be unrelated problems. Okay, so remember, ladies and gentlemen, for Wednesday, you have a free day. There is no lecture. You can use that at your discretion. The test for WebAssign will be available on Thursday. You will have till Saturday at 11 p.m. to complete that. This is giving you plenty of flexibility. And just remember that all of this material will be next week. So once you finish your test, you get busy on the work problems, do the homework, and there won't be a quiz on this next week. We won't have a quiz next week to give you a break, and then the quizzes will start back up, but your homework on the work will be due. So again, once you finish your work for this test and you knock that out, then we'll get back started with this. And then the next topic will be center of mass, and then we'll hit some integration review and integration techniques. I think you'll like the integration techniques. You'll probably find them to be a little bit easier than this, because this just uses all kinds of algebra and things that may be a little bit different, but I think everything is good. So I appreciate your time today. Hopefully you enjoyed the applications with the work problems. I think they're very neat and fun to do. And trust me, this is just the tip of the iceberg. You can do more and more of this as you take engineering and physics. So everybody have a good day. Good luck with your work. And I'll see you at office hours. If you happen by, I'll send out some invitations. Have a good day, everyone.
Thank you. Have a great day.
Thanks.